Hello and welcome to the first of hopefully many videos on, physics. Well, not only physics, I hope to bless your ears with other things like reading books, maybe sci-fi or philosophy or history, etc. But also computer science and mathematics videos. Well, as you can see, there is a little VTuber avatar in the bottom left, and I hope to explain some different concepts in physics. Well, if you are a big physics head or a physics nerd, I am incredibly sorry if you see this as boring or old content that you may have covered, or even then, some of this stuff is stuff that you go over in high school or secondary school, but for a lot of people they don't really have physics or listen in physics lessons in those lessons. Well, this is a book, probably one of my favourite physics books, because I get the rereadability of it. On the front cover here, you have things like chaos theory, or in popular culture known as the butterfly effect, as it looks like a butterfly wing. You have relativity here and gravity. You have Schrodinger's cat. I call it Schrodinger's cat, and I get told off for calling it Schrodinger's cat, even though I can speak German. And here is just a butterfly, which I believe is linking to the butterfly effect, or is some form of symmetry. Well, we open this up. There's the Large Hadron Collider in the Geneva, France border. See, this is what we are doing today: classical mechanics, also known as Newtonian physics. So I thought I'd give this a little read. Mechanics is the field of physics that concerns itself with the behaviour of objects in motion, or subject to forces. With its origins dating back to ancient Greece, it is the oldest area of physics, and is referred to as classical because it involves laws that were understood long before the twin 20th century scientific breakthroughs of quantum theory and relativity. These laws can be still applied to explain most common phenomena in the universe that occurs from the scale of the atoms and molecules upward. Well, here this is slightly wrong. I believe quantum physics as a whole is applied from C60, so a very complex larger molecule of carbon, all the way down to gluons, quarks, but I will not get into gluons and quarks or large molecules of carbon. It is only in extreme situations involving high speeds, strong gravitational fields, or very small scales, the more recent breakthroughs offer a more accurate description of what's really going on. Classical mechanics describes the aspects of the universe that range from simple machines to the orbits of planets and the properties of solids, liquids and gases from the atomic level up to everyday or macroscopic scales. Underlying all these different phenomena is an elegantly simple model of colliding bodies and simple laws that govern their interaction and behaviours. The techniques of classical mechanics allow us to calculate the gain, loss and transfer of energies between particles and to predict their behaviour in a variety of situations. The most important of these laws are Newton's laws of motion and gravitation, described by English physicist Sir Isaac Newton in his 1687 book on the Principles of Natural Philosophy, best known for its Latin title simply the Principia. Newton's laws describe the motion of objects under the influence of forces and the strength of the attraction of gravitational forces between large masses. As such, they provide a complete description of many natural phenomena that only breaks down in extreme conditions. On the submicroscopic scale, the quantum physics, or in situations of extreme speeds or gravity described by relativity. Indeed, Newton's laws do such a good job of describing the everyday world around us that Newtonian physics is often used as a synonym for the entire field of classical mechanics. So that is the mechanics introduction in this book. I'll also show you the back here. This goes into my little book pile on my desk, but also there is an electronics kit on there as well. But here I have a power supply right here that I've screwed into my desk. I use a old computer power supply to power it, but that is for another video. But today I'm going to firstly show you as in what the book said about Newton's Principia, the principles. You have his first law of motion, which states that an object remains at rest unless a external force is applied to it. This, for example, this part is very intuitive, but remember, Newton at the time was going by what he saw in his surroundings, his interpretation of the world around him, and that's what Newtonian physics is very good for, our own personal interpretation of the world around us, as the realities are quite a lot more complex than this. But we have a box here, and let's say we add a force, and we're denoting force by F. Obviously the box will move, but let's say, for example, there is no force applied to this block, box at all, no, not even gravity, this object will remain at rest. And this fundamental law here allows for, quite simply, satellites to move. You see, I'll draw it. We have the Earth here, and let's say we have a probe that we're trying to send out to, let's say, Saturn, and Saturn's really far. Let's give Saturn its lovely ring. And this is what NASA did when they sent the Voyager probes. I know that NASA currently are making a Europa probe, which I may do a video on, like NASA and even the Soviet space industries and what they've done. I've actually myself have ordered this lovely Venera 5, which was a mission to Venus by the Soviet Union badge. But anyway, back on. So I believe it was the Voyager, one of the Voyager probes. I know there was 2 set out, and one went all the way to the sun here. This is perspective wise, I don't know why the sun's smaller, but anyway. So the Voyager probes, they basically slingshotted around the sun's gravity, allowing it to gain like a large amount of force, or what technically would call velocity, but I'll get onto that in a minute. But they slingshotted it, and because space is a vacuum, there was no other forces acting on the probe. Well, there would have been a few, but simplicity's sake, and causing the probe to slingshot around to Saturn to study Saturn's moons. And that's how this first law of motion is used today, but it's used in many other cases. You have the second law, which is the most famous second law, which must be simply explained as a force is equivalent to its mass, the mass of an object, times its acceleration. And the units for force is equivalent to a Newton. And in Newton, well, we derive a Newton, so something called SI units. And this is what the standard governing body is for units, and this basically body says which is a non-derivable unit, which is the base units, and which can be derived. So the force, the Newton, can be derived as just, well, kilograms meters per second to negative squared. This, if you didn't know, basically just means that, well, if you had one times 2 to the negative 2, that would just be 1/2. So that would be just 1/4. That's basically what that means, that power, the negative power. And that is then a Newton. And this is probably the most fundamental equation in physics, basically, because you can derive from this. Weight is equivalent to the mass times the gravitational acceleration. So on Earth that'd be 9.81 meters per second. squared. Now, that is just some notes I have for later, some like numbers for a question we should do in a bit, but the third and final law in Newton's principle is that for every force, a equal opposite force exists. So, what this means is that, well, I remember it in a textbook that I had for my GCSEs, when it's explaining the third law of motion. It had a man, and he was pushing his little shopping trolley across. It looks more like an open box. Just imagine this as a shopping trolley, and he was pushing the shopping trolley with force, and the man with arms will then experience an equal opposite force. So another example of this is that when you're standing on the ground, you don't fall through the ground because you have mg, mass and the gravitational acceleration. You also have mg being put back on you from the ground too. So from these, we can now go into more complex aspects of physics. So what I would like to get onto first is to what everything in physics can be derived as, like all the units can be described as vectors and scalars. So if you ever watched Despicable Me, and you had Vector, and he was the bad guy, and he said direction and magnitude. Well, that's what a vector is. It has a direction, so it has a direction and a magnitude. So one example of this previously, acceleration. And we denote vectors by underlining them or putting an arrow above them. But I won't be doing that for all of them. We also have velocity. We have force. And displacement, which is like, say for example, I go to the shops and I then walk home from the shops, then my overall displacement will be 0, even though I may have gone a couple of kilometers to the shops. And that gets onto distance, speed, their scalars, say resistance even, that is a scalar that doesn't have any direction. Over here you could say current can have a direction, but also, with an alternating current you can have a direction. So potential difference. So these are two you can derive everything from. And so ruler. This ruler here. I got it probably when I was about 7 from Smiggle or whatever, or whenever. I don't know. It's got dinosaurs on it. You know, early solar system, but anyway. So let's say we have 2 forces acting on an object. So we have 6 newtons acting in what we would call in the y component, and we have 4 newtons in the x component. You see, if I move this object, like, oh, sorry, you won't be able to, like diagonally, or if I throw a ball and it has what we call a parabola, I think I said parabola wrong. I'm incredibly sorry if I did. Dyslexia. Well, the y component and the x component completely separate. And I will show you a video now which proves that from the most excellent Walter Lewin. So as you saw from that video, the ball travels, but also it lands in the same place that it was shot from. So as the contraption moves, it still caught it. Of course I had a funnel because everything has uncertainties in physics. But let's go on to our vectors here. So to simplify the magnitude of both of these, you draw a triangle, and to find this you would just do square root of 4 squared plus 6 squared. Now, do this on our handy dandy calculator. I've had this calculator for a very long time, as you can tell. Oh, I did squared there, not square. It's cubed, sorry. You can tell it's all worn down because I've used it quite a lot. That is the magnitude, and it is in a third form, which means that it's its exact form, but it's around 7.2. And so that is 7.2 newtons. That object will move. Now, to find the direction of that object, we get it from theta here, which would be cosine. Well, so we have the adjacent and the opposite. But we also have the hypotenuse, so we can just do 4 over 7.2. I believe this would be greater than 45. Wait, no, it should be less than 45. Oh, sorry, I just did the cosine, not the negative cosine. And greater than 45. God, trig constants. I'll quickly go into trig constants because why not? So the cosine of 0 is equivalent to 90. The cosine of 30. Oh, 30. You can use your hand, so that would be square root of 4 over 2, which would be 1, but be equivalent to 90. Oh no, sorry, not 90, sorry, 1. Gosh, that's the sine of 90 is 1, but so 1. I don't know why I said 90, but the cosine of 30 is a half, as you have 1 over 2. Oh no, sorry, cosine here, and that's sine. As you can tell, your trig constants you can get messed up very easily, and etc. I can't be bothered to go into them more. I would recommend, if you want to, you can research trig constants, but theta is 56.3 degrees. That object is travelling, which makes sense as 6 newtons is more in the y component. Well, that's vectors, and that's how you derive vectors. And as I said before, if you have a parabola and you want to find the distance of that parabola, you just get the x component to find the distance of that object, the displacement of that object, not the distance is travelled. That would be a bit more complicated. And so now I want to get on to something called momentum. You might have heard this before, especially if you've done physics, but momentum is derived from P is equal to mv, with P being momentum, m being mass, and v being velocity. And so you can derive the units in SI units for momentum as being kilogram meters per second. And so I did have some numbers jotted down. Let's have a look. Yeah. So let's say, for example, you have a TGV duplex. A TGV duplex is a high-speed train run by the French National Rail Company, and it is very interesting because it is double-decker and can go around 600 kilometers per hour. If you've seen the test video, if you see the test video of this train, it whizzes past, it goes when they were going 600 kilometers per hour. They had to stop it because they were worried that it was going to fly off the tracks. They were worried that the air underneath it was going to cause an uplift on the train, and it was going to fly off. Not literally, but it would like start to become very unstable. Draw little pantographs and it's going into the SI units. But anyway, let's say there's this train, and this is 380 tons. That's 380,000 kilograms. And let's say there's this Fiat 500. It's my lovely drawing of Fiat 500. There's an angry Frenchman in it because he is driving a Fiat 500 and nobody wants to drive a Fiat 500. And that is 0.98 tons. So 980 kilograms. Well, of course, this train is going to plough into that Fiat 500. But, well, how will that affect the train's velocity or kinetic energy? You know, you have energy in form of electricity, but moving objects, like this calculator, as it falls, it gains kinetic energy. Obviously, as it hits my desk, it loses all of its kinetic energy. But, so we shall work that out. So, firstly, we've got the right units for mass here, but we know that this train, let's say it is going from Paris to Geneva, and it is ploughing down to Lyon, down the high-speed line there. And this angry Frenchman in his Fiat 500 is stuck on the tracks, but because he's so angry and he's uncool to one of his friends, he's shouting at them, he's forgotten that he's on a high-speed track. He's about to be, hopefully, not killed. Maybe, though. And so the kilogram is our unit of mass. Velocity, but our velocity should be in meters per second and in kilometers per hour. So to do this, we need to go from kilometers to meters. So we go 320,000 meters per hour. We need to now divide this by 60. Divide it again by 60. And we get 89 meters per second. To get the momentum, we times that by 380,000. You know, it's going to be a very large number. So the answer would be 89 meters per second. And so we would want to the answer is 89 meters per second, and so we would want to 89 meters per second times 380,000, and that gets a very large number. 33,820,000, and that is kilogram meters second. And now we would want to add the weight of the Fiat 500, so it would be 380,980 kilograms, and then we would want to divide it by want to divide this by 30,820. No, 33,820,000. 33,820,000 over 380, 980. Sorry, also, if you notice I cut out quite a bit, it's because my mum is, I think she's packing things in the background, or I don't know, doing something in the background, I'm not entirely sure. But I had to cut out when she's like walking by my room and things, and so I'm very sorry if you do hear that. Well, that gets us relatively the same velocity. You see, the FID 500 has barely affected the momentum of the train, because it is not moving and it is at less than a ton. So we'll just say that's 88.8 meters per second. So that is literally a change in 0.2 meters per second. Well, you could have a look at the change in kinetic energy if you wanted to, because that might be something interesting. So if we times that by 380,000, we get believe that's 33,000. Oh, no. Right. I've just realised I did that wrong, and I forgot to tell you the equation for kinetic energy. So, kinetic energy is equivalent to half times mass times velocity squared. And the units are the same for the SI units are the same for the units for joules, and you just don't care about the half. You do kilograms, meters, second squared. So that gets you kilogram meters squared -2, and that is the unit for joule, which is the unit for kinetic energy. So go to our calculator. If we do 88.8 times, squared times 1/2 times 380,000. Then that is our final kinetic energy. That's 149 million. No, that's 1,498,000,000. No, that's 4. No, it's quite hard to tell. No, so 1,499,233,000. 233,600 joules. So that's 1.4 gigajoules of energy. That's a lot of energy. And that is our final. Source. So we'll shall let's drop that from the initial, which would be that times 89. That is 1,504,990,000. Subtract that from 1,498,233,600. We get a change in kinetic energy 6,756,400 joules negative. Oh, you cannot see that. I'm incredibly sorry. So, see that? Yeah, I will change the page now. Sorry, I get very into it when I'm working out. So as you can tell, the Fiat 500 did not affect the train's velocity or kinetic energy as much, but I shall now get into, see my keyboard there. So another thing you can do with kinetic energy is you can find the maximum height an object will be until it will. So we have a ball, and it has a very funky arrow, isn't it? And it has an acceleration upwards. So it has a kinetic energy and acceleration, but I'll just screw it out. And when that kinetic energy is 0, that is when what we call gravitational potential energy is going to be its max. So gravitational potential energy is weight times height, and obviously weight is equal to mg, so it's also equivalent to mgh. Usually it's denoted as that, but weight and gravitational potential energy are very similar. And this is also in joules, because it's energy, gravitational potential energy. Sorry if you can hear me hitting my microphone sometimes. I'm sort of hunched over here. So let's say we have a 500 gram tennis ball, and let's say we got we throw it up with 5,000 joules of kinetic energy. No, scratch that. Sorry. Scratch that. Let's say we throw it up with I'm coming to the top of my head, so I'll just say 15 meters per second. It's maybe very strong for someone to do this, but I don't know. So that is 0.5 times 0.5 squared times 15. Times 15 squared times that's it. I've got keeping track here. I'm sort of rushing that, am I? That's not very good. You don't want to rush things like this. Squared times 15 squared. So that's apparently half times 56.25 joules of kinetic energy. Then you go 56.25 is equivalent to mass mgh. So we fill it in, so we go as you can see now, didn't make this obvious earlier, but as you can see, mass doesn't matter here. We just need g, h, and the velocity, and so times g, and that's 9.81. So we can divide this by 5. So that means that, and if we divide that by 9.81, that means that the maximum height this ball will go is 11 meters, or 11.5 meters in the air. Now, I'm going to get a physics book, not this one, there's a calculus book underneath that. Place that over here. I also have some these are some jumper cables, and I may do a video on the Arduino, maybe. I may do a video on the Arduino too. Struggling to find places to put this. There, I'll put it there. But this is what I wanted. This is quite an old book, as you can tell. This is A-level physics. Obviously, I'm not going to use this for actually revising for A-levels, as that would be plain darn stupid. But we have vectors here, as you can see. Obviously this is in a more mathematical format than what I was saying. Displacement. Now this is very interesting. This is tension, and this is similar to vectors, so I think I will do this question here to finish off. I'll get a clean page. Hit the microphone there. So, I know to the dismay of many, if I can find where is my ruler gone? There it is, under the book. Got the ruler. So, let's draw this diagram out. So, we have a tension here. We have tension here. And these two different tensions have 60 and 30. I think I will divide these up into triangles. Makes it easier to see. I need to put my microphone somewhere else. I keep on hitting it. I'll have to cut that out whenever I hit it. But there. And we have a mass here, which is rather small mass, 1.2 newtons. Well, this means that we have T2 here, T1, so that means T1 plus T2 is equal to 1.2. Well, of course, if we want to find the different components, we will obviously need to find the different components to find T1 and T2. Now I'm having to work this out. This is a bit more difficult. So I have just realised that it is here. This is 1.2. So I did that wrong. It will be T1 cosine cosine 30 plus T2 cosine 60 is equivalent to 1.2. So that now if you have your truth constant, let's get a handy dandy handout. The cosine of 30 is equivalent to a half, and the cosine of 60 is equivalent to square root of 3 over 2. Now, if we want T1 and T2 by themselves, 1.2 divided by 0.5 equivalent to 2.4, of course. Divide that by equal the square root of 3 over 2. Now we know that T1 plus T2 is equivalent to 2.8. Now, also you can write that these two are equivalent. So T1 cosine 60 is equivalent to T1 cosine 30. I'm sorry, I'm getting my T's and I'm going to close the book here because I've just realised in the corner of my eye you can see the answers, and I don't want to see the answers just yet. I do want to work this out. So we have worked out that these are equivalent. So let's get T1 on the same side here, so T1 is equivalent to 2.18 minus T2. And over here, if we want T1 on the same side, we go T1 is equivalent to T2 cosine 60 over cosine 30. And you can cut this off here, just have T2 times cosine 60 over cosine 30. And I've technically already done this, but I will show on the calculator. That's square root of 3 over 3. So T2 square root of 3 over 3 T1. So now, because we have T1 here, I have 2.18 minus T2 is equivalent to T2 square root of 3 over 3. Now, here's a problem. We have a minus here and a multiplication here. Now that is a problem. Well, what we could do is divide T2 here. We're going to need to get rid of one of these T2s. So 2.18 is equivalent to T2 plus T2. So that means that 2.8 is equivalent to something plus, but that's not good because we have two of the same variable on the same side. Well, we want to get T2 on it by itself here. So we can try and factorize this. So we have T2 square root of 3 over 3 plus 1. Now we have 2.18. Oh, I've smudged it there. Over 3 over 3 plus 1. Oh, I'll put that in brackets, why not? So 2.18 over square root of 3 plus 1. That is equivalent to 1.4 newtons. Because I'm just going to round it here. 1.4 newtons. So T2 is equivalent to 1.4 newtons. Now, how will we find T1? Well, we could come back over here, and now that we've got T2, we can multiply T2, which is 1.4 times the cosine of 60, and that is 0.7. So 0.7. So that means that T1 cosine of 30 must be equivalent to a half. And so we can just do T1 is equivalent to 0.5 over cosine of 30. And I think there's going to be something very wrong that's about to happen here. Nope, I was wrong. Instead, I've got that T1. Actually no, we worked out T1 earlier. I think I may have done something wrong here, but I believe I haven't. But if I have, and I've just realised I haven't shown you all my working out here, I'm so incredibly sorry. But you can see here. But I've explained it. T1 is square root of 3/3. And well, this side is a lot smaller than that side, wise, so I'm guessing that, and it's got less of an angle, theta, so I am guessing that that is correct. And if we go back to the book, the handy dandy little A-level physics book, 2nd edition, with harmonics here. Well, I'm guessing that they, as you can see here, I'm not far off, 0.404, so I'm guessing that I rounded up everything and they didn't. But to saying that this is not an exam, I do not care, and I would have liked to round everything up because I don't like using exact values. Either that or I went slightly wrong somewhere, and if I did, please feel free to tell me where exactly I went wrong, because we're all learning here. But I don't think I did, and well, with that, I would like to say that if you have got this far, I don't know how you have, because apparently I'm quite annoying, so, well, thank you very much, and I hope that you have a good rest of night, day, evening, whenever you are watching this, and if I have more videos in the future, I hope you enjoy those as well, and I hope you have a very good rest of whenever, and I hope you enjoyed the physics as well, as I think it should speak for itself other than me. So, goodbye then.